First things first, let's just tie up some loose ends from last time. We were talking about the 9-point circle. This circle associated with any triangle, its existence is actually kind of astounding. That always goes through 9 different points. We've got the three medians of each side, we've got the 3 feet of the altitudes, and 3 so-called Euler points. And the fact that they all lie on a common circle is really quite astounding. So anyway, we proved the existence of this circle, except we had a couple of claims that we didn't write down the proofs for. I'd mentioned how to do them at the end of last class, but let's just quickly sketch out the details. And to start, we'll just redraw our picture. A, B, C, there's the triangle ABC. We called the feet of the altitudes, we called these D, E, and F. D, E, and oh boy, this is going to come very, very close to the median. That's okay. D, E, and F. Okay, we called the midpoints of each side, we call these P, Q, and R. P, Q, and I'll put it just below there. The orthocenter is of course H, as always. And then we had our 3 Euler points, so those are the midpoints of AH, BH, and CH. So midpoint of AH, we call that X. Midpoint of BH, we call that Y. Midpoint of CH, we call that Z. Is there anything else I want on here? Yeah, I suppose I'll draw on exactly what we had last time. We had looked at, do I still have my colored chalk? We had looked at this line segment here. This was sort of the crux of our whole proof. We had looked at this line segment YQ. So connecting this Euler point to the midpoint on the opposite side. And we had shown that the circle that uses YQ as a diameter, or has YQ as a diameter, is in fact the 9-point circle. Right? It's a circle that goes through all 9 of these points indicated on here. And the way we had done that is we had made this claim that this angle here, YPQ, and this angle here, YRQ, we made this claim that both of those are right angles. If this is a right angle, then this is a right angle triangle, so its hypotenuse is the diameter of a circle containing all 3 of those points. Therefore, it is the circle we're looking at. It's a circle that uses YQ as a diameter. So we'll prove these claims. Proof of claims. And claim 1 was, what was claim 1? Claim 1 was this angle, YPQ. Angle YPQ is 90 degrees. So I mentioned that this is really just an application of our lemma involving similar triangles and parallel lines that we've used over and over again. Actually, lots of ways you can prove this, but here's one proof. I want to prove that this line PQ is parallel to AB. Well, the way I can do that is I know that CQ over CA, since this is a midpoint, that's 1/2, and CP over CB, P is the midpoint, that's 1/2. So by our lemma, PQ must be parallel to AB. Okay, so CQ, this is really just a sketch. I'm not going to write down all the words or anything, just a sketch. CQ over CA, that's 1/2, which is CP over CB. So invoking the lemma, that means that PQ is parallel to AB. And therefore, because this is a right angle, right? CF is an altitude, because that's a right angle. This is a transversal of two parallel lines, so because this is a right angle, that's a right angle. And those are alternate interior angles. In fact, I suppose this one's the alternate angle, but if that one's 90, this one must be 90 as well. Right, so I won't even write the words. Like I said, this is just a sketch. That implies that angle VRC, we'll call it, which is 90 degrees, that equals angle, let's call it FZP. So now I just want to do the same thing over here. I've got a transversal. If I think of PZ as a transversal, I want to show that these two lines, YP and ZR, I want to show that these two lines are parallel to get, that's a right angle there, by transversals again. So what triangles am I going to look at? I believe I'm going to look at this triangle. I'm going to look at this triangle of BHC. So that's the triangle we're going to focus on. And what do I have? I think I have to turn my head here. So I'm thinking of this as sort of the peak vertex, and this is the base, if you want. Right, so By over Bh, well, y is the Euler point, right? So the Euler point is midway between B and H, so By over Bh is 1/2. Also, By over Bh, that's 1/2. Yes?
Can you not say FZP?
F?
Isn't Z not the point?
Oh,
that
yeah.
that line goes through?
Wait. Yeah, so it's F some point. It's whatever this point of intersection is, right? Clearly it's a point of intersection, so good enough. Yeah, that's a good point. I was, again, looking at my diagram and just assuming I was missing this, but you're absolutely right. It doesn't necessarily go through this Euler point. So anyway, so By over Bh is the same as Bp over Bc. Both of them are 1/2. And that then implies that Yp is parallel to Hz, if you want. And go Yp parallel to Hz. Or how about if I'm thinking this is the base of the whole triangle, Yp would be parallel to Hc. It's obviously the same line, but I'll use consistent naming there. And yeah, now we're done. So now we're done. We have that this angle we looked at, F, some unknown, or not unknown, but unlabeled point. This is a really terrible notation, by the way. But this angle F question mark P, which was 90 degrees, being that this is a transversal between parallel lines, this angle here must be 90 degrees. So the one we wanted, YPZ, is 90 degrees. established. But that's a right angle. The proof for the other angle is similar. You just have to invoke the lemma on the right sides. There's too many lines in here. I always get tripped up as what I'm trying to figure out for which lines I should use. So I'll just quickly point out the correct lines. Let's see. The other one, claim 2, is that angle YRQ is 90 degrees. And according to my notes here, I've chosen this one. I've chosen AR over AB to be 1/2, which is the same as AQ over AC. Just blindly believe in my notes here. Let's look at this. AR over AB, R is the midpoint of this side, so AR over AB is 1/2, and that's the same as AQ over AC. So that's pretty obvious. So what does that mean? That means that side there is parallel to that side there. And so RQ parallel to BC. And my other claim is that BR over BA is 1/2, which is BY over BH. We'll see if that's true. So B to R over B to A, that's 1/2 clearly. Claims that this is the same as BY over BH. So yeah, so now we're looking at this triangle here, AHB. Because both of these are 1/2, that means that this line connecting Y to F, so YF is parallel to AH. I said YF. Problem is my picture here is so cluttered. F was the foot of this altitude. It's actually YR, right? It connects to the midpoint. So YR is parallel to AH. Is that enough? Is that what we wanted? My picture is very cluttered here. YR F. Oh, we are looking at this angle. Why would it follow? Oh, well, AH, we've shown that that's perpendicular to BC. We haven't even shown that. That's just by definition the fact that this is an altitude. So now, because AH, if you extend it anyway down to AD, that's perpendicular to BC. So that's a right angle, so this is a right angle. And then by parallelity of these last two lines, yeah, we've established it. It's the exact same argument as before. Just trust me on this. You can double check these details if you want. I really wasn't even going to write down a second proof. H is perpendicular to BC, so the result follows. Angle YRQ is 90 degrees. I would need to redraw this whole thing to make it look sensible. How many other ways can you do this? Lots. If you look up proofs of the existence of the 9-point circle, there's a whole bunch of them. This is the one the textbook goes with, though I like it a lot. I think it's kind of sleek and clean. And one of the things about geometry is, if you find alternate proofs online somewhere for something like this, usually it will depend on the order in which the material is developed, right? You might see someone else prove this using theorems from later on down the road that we haven't proven yet. So the proof, of course, has to depend on stuff you've already done, and this is just invoking that lemma that we've used over and over. All right, so we have that. Proof of the second claim wasn't the cleanest, but it really is the same idea. So I'll just state two more theorems. I mentioned them last class, but the question is, what's the radius of the 9-point circle, and where's the center of the 9-point circle? So the center, N, of the 9-point circle is the midpoint of O and H. So that's pretty astounding. It was already quite astounding that the Euler line, which as long as you have two separate points, you can draw a line through them. So it's not too interesting that Euler line passes through O and G, which is our definition. Right? Any 2 points has a unique line passing through it. But it was somewhat astounding that H, the orthocenter, also lies on there. That all three of those points are collinear. Well, this is doubly astounding now that this 9-point center we define, its center, or a 9-point circle, its center, N, is also on that Euler line. And just to recap how everything relates here, so we have O, the circumcenter. We have G, the centroid of the original triangle. Where does H live? Well, in proving that H was on the Euler line, we did even more. I showed you exactly, we proved exactly where it was. It's collinear with these guys, and it lies on the opposite side of O and twice as far away. So there's H. And now this theorem says that the center of the 9-point circle is exactly midway between O and H. So here's N. That means that they're all actually sort of equally spaced along this line, right? This distance, well, how would I say, this distance is twice this distance, so H to N is exactly the same as N to O, exactly the same as O to G. And they're all 1/3 of that line segment. And I mentioned this last time in the encyclopedia, what's called triangle centers. O, G, H, and N are, I think, centers 2, 3, 4, and 5. Not necessarily in that order. So there's still center 1, the big one, that we haven't talked about yet, but we will soon enough. And the other thing is, what's the radius? Well, we know what the diameter is, right? The diameter is the line segment, or the length of the diameter is the length of the line segment connecting an Euler point to the midpoint of the opposite side. The question is, what is that actual length? And it turns out that the length of that diameter is the same as the circumradius of the original triangle. So the radius of the 9-point center is r/2. Let's see. The radius of, did I say 9-point center again? The radius of the 9-point circle is r/2. And by big R, I of course mean the circumradius. Circumradius of the original triangle, ABC. We could prove these facts, but proving them would probably take us all class. I don't think it's worth doing. There's really no nice way to do it. You tend to have to invoke transformational geometry, and I don't think we'll ever have to use it anywhere else in this whole class, so it's really not worth talking about. That's the proof the author goes with. I looked online to see if I could find something else that was nice, because it's actually not easy to prove. But just about everyone proves it that way because it's by far the best way to do it. So just accept these. You can read the proof in the textbook if you want, but we're not going to prove them. Any questions? All right, let's work on a problem here. How about a 2C.2? Show that the circumcenter of triangle ABC is the orthocenter of the medial triangle. I don't like that he's called this the medial triangle. I guess it's obvious, but it depends on ABC, so let's call it its medial triangle. And so we have our triangle ABC. This is circumscribed by its circumcircle. Looks like in my picture, well, let me not indicate it just yet because it's not going to line up correctly. And then we've got the medial triangle. So take the midpoints of each side, X, Y, Z. And we want to show that the orthocenter of this medial triangle is the same as the circumcenter for the triangle ABC. It's the center of this circle. And I'm in no rush at all today, so spend a few minutes, think about how you might prove this. And if you're stuck, I can give you a hint in a couple of minutes, but I don't want to give you a hint right away because there's so many ways to prove things in geometry that curious to see if you come up with another direction than I have. So my hint is ask yourself this, how do we find the centroid? We look for the concurrence point, the concurrency point, the point of intersection between the medians, right? How do you find the orthocenter? You look at the point of intersection between the altitudes. How do you find O? How do you find the circumcenter? Well, of course, it's the center of the circle, but how do you find O? Because it is a point of intersection between three different lines. And that goes all the way back to proving first that every triangle is indeed inscribed in some circle. So if you'll remember, that if you have a triangle, the way you prove that it's inscribed in some circle is you go to each side and you look at the perpendicular bisector of each side. Right? So you drop in perpendicular bisector of each side. And that point of intersection between perpendicular bisectors, that is the center of the circumcircle. Well, what if I draw altitudes from z, y, and x? It certainly looks like those are perpendicular bisectors of AB, BC, and CA. Well, by definition of being altitudes from x, y, and z, that is the orthocenter of that medial triangle. If I can prove that they're also perpendicular bisectors of these original sides, then we're done. Because their point of intersection is actually O. Right? And that's not hard to do. But that was my thinking. Anyone have a different idea? Okay. So yeah, maybe we'll sketch a proof of this. And now that we've figured out the details of what we want to do, we'll write this in the order of a nice clean proof as opposed to the order that we think about things, which is I'm going to jump straight into proving, for example, that the altitude from Z is the perpendicular bisector of AB. How am I going to do that? Well, as always, we have that this line segment here, CY over CA is 1/2, CX over CB is 1/2, so XY is parallel to AB. By definition of being an altitude, that's a right angle. So alternate interior angles, that's a right angle. It's perpendicular, it cuts through the midpoint Z of AB, therefore it is perpendicular bisector. So CA over CY is 1/2, which is CX over CB, and that implies that XY is parallel to AB. I need a point here if I'm going to refer to it, so let's call this point, what do you want? Let's go PR and Q, so we'll call that point P. Let ZP be the altitude of the medial triangle XYZ from Z. Angle ZPX, by definition of being an altitude, that's 90 degrees. Which implies, by the above fact that these are parallel lines, that implies that AZP is also 90 degrees. transversal of parallel lines. If I know this angle, then I know the alternate interior angle. And that means, again, maybe I should just call this a sketch of a proof because I'm not really fleshing it out as well as I should. But that means that that ZP is the perpendicular bisector of AB. ZP is the perpendicular bisector of AB. Similarly, the other altitudes are perpendicular bisectors of the other sides. So similarly, the other two altitudes are perpendicular bisectors of BC and AC. So the remaining two sides. So their point of intersection, which by definition is the orthocenter of the medial triangle, is also the circumcircle of, or the circumcenter of ABC. So their point of intersection which is the orthocenter of XYZ, is also, being that they're perpendicular bisectors of the sides of ABC, is also O, is also the circumcenter of ABC. So not hard. I'd be curious to see an alternate proof, but this is what I came up with, and once you sort of go down one road, it's hard to start backtracking. But this of course heavily relies on the fact that you know how to find the circumcenter. And I'm reminding you here because we usually think of orthocenters and medians as being concurrency points, but or points of concurrence. But yeah, O, the circumcenter, is also a point of concurrence between three lines, and it is the intersection of the perpendicular bisectors. And what I was hoping to do now is jump straight into what's called the in-circle and the in-center, which is the first triangle center in that encyclopedia that I've mentioned, of triangle centers. But there's a lot of stuff there that to prove it, you really sort of need to invoke Heron's formula. So I can't jump straight into it like I wanted to. I can't just sort of skip over the section, maybe come back to it later at a better time. We're going to have to cover some of this stuff now, hence the reason why the author of our textbook throws it in now. This is computations. So these will be nice equations, relationships between sides of triangles and so on. Things like one of the most famous computations with triangles is the Pythagorean theorem. And we'll jump straight in with one you've already seen worked with a million times, but this is the law of cosines. And because you're so familiar with it, I'm not even going to write down all of the details or anything. I'll just remind you what it says, which is if I have a triangle, doesn't have to be right or anything, just if I have a triangle, ABC, If we label the side lengths of the opposite sides as usual, so side opposite A, B, C has length A, side opposite B has length little b, side opposite C has length little c. Then, what does the law of cosine say? Do you guys remember this one by heart? I often forget it, to be honest, but it says this. It says c squared. So this side length is a squared plus b squared minus 2 times a times b times, not sine, it's the law of cosine, cosine of angle c. And I want to point out something sort of special here that's happening that maybe you haven't thought about, is this looks a lot like Pythagoras' theorem, right? Like the Pythagorean theorem. Pythagorean theorem applies for right triangles, in which case we just have c squared is equal to a squared plus b squared. Here we have sort of c squared is a squared plus b squared, but with this extra little correction term on the end, right? Minus this extra correction term 2ab cosine c. And in the event that we have a right triangle, well, imagine this is the right angle. In the event we have a right triangle, cosine of 90 degrees is 0, right? So in the event of a right triangle, that term disappears and you have the Pythagorean theorem. So the Pythagorean theorem is really just this special case of this theorem. This is the more general version, and I always think of this as being sort of a correcting factor, right? It's if you're not a right triangle, then you don't quite have the Pythagorean theorem, you have almost Pythagorean theorem with this extra correcting term on the end. So we'll just point out that the Pythagorean theorem is the special case. Where C is 90 degrees. Because it looks so much like Pythagoras, that should sort of give you a hint that one of the ways we might want to proceed is by using Pythagoras. And how would you do that? Well, you could drop an altitude in here and then work with right triangles. So that's exactly how we're going to prove this. Which happens often in mathematics, that you prove a special case and use that special case to prove the more general case. So here's our proof. I guess there's 3 cases. We'll do an angle C less than 90 degrees, bigger than 90 degrees, and equal to 90 degrees. And we'll knock out the easy one first. Angle C equals 90 degrees. Well, then we just have Pythagoras. And we're done. Case 2, let's do the acute case. Angle C less than 90 degrees. So we have a picture basically like I just had. A, B, C. So this angle here is less than 90 degrees. And we'll drop in an altitude and call that altitude H. So it is possible, if this is an acute angle, it's possible that A or B, I haven't drawn it like this in this picture, but it's possible that A or B, one of them is bigger than 90 degrees, right? That's possible. It could be like 90 degrees and 5 degrees and 85 degrees or something. But what's not possible is that both of these angles are bigger than 90 degrees, because angle sums of triangles are 180. So one of them has to be acute, at least one of them has to be acute, and we'll just assume without loss of generality that it's angle B. Okay, so assume Right, one of them has to be acute, so if it's not angle B, relabel everything so that it is angle B. Assume, without loss of generality, that angle B is less than 90 degrees. The foot of this altitude here, we'll call it P. So we'll say that AP be an altitude. And let's let the length of this side, so BC has side length A, but PC, we'll just call it X. So let X be the length of PC. And we just have to do one more thing here before we invoke Pythagoras' theorem, which is do a little bit of triangle trigonometry on this. Cosine of C. What's cosine of C? Cosine of C would be, that side length is B, cosine adjacent over hypotenuse. So cosine of C would be X over B, right? Now, cosine of C is X over B. So that means that B times cosine of C is X. And all we have to do now is actually invoke Pythagoras' theorem twice. So by Pythagoras, x squared plus h squared. What's that? Well, this is a right triangle, so x squared plus h squared is b squared. Right? And we'll do the exact same thing over here with this right triangle. So this side length would be this whole thing. That's a, right? So this guy here would be a minus x. And a minus, oops, other way around. A minus x squared plus h squared is c squared. What did I want to do? I wanted to prove the law of cosine says that c squared is equal to something, right? So let's take this point here. We've got c squared is equal to something and try to manipulate the left-hand side. So c squared is equal to, we'll FOIL this out, a squared minus 2ax plus x squared plus h squared, but we're going to make a substitution at this point. And again, if I was sort of writing this down really nicely, I should invoke the fact that I should sort of write down somewhere that I'm substituting it in this equation. But plus h squared. So what's h squared equal to? That'd be b squared minus x squared, right? So those cancel. The x squareds go away. I'm trying to prove the law of cosine, which says c squared is a squared plus b squared minus some correcting terms. So let's just rearrange the order that we've written this in. This would be a squared plus b squared minus 2ax and now we're done. What did we say x is equal to? A little triangle trick. X was b cosine of c. So this is a squared plus b squared minus 2ab cosine c, which is the law of cosines. Last but not least, I guess we won't prove it, we're pretty much out of time here, but case 3 is angle C bigger than 90 degrees. So you end up looking at something like, triangles will look kind of like this. In fact, both of these must be acute in this case, right? So angle C is obtuse. Well, what do? You do the exact same trick. You say, I'm going to drop an altitude there. Turn this into a right angle. I still have H and so on. The details are very similar. We won't go through it, but it is in the textbook if you want to see. So this is similar. See text. I probably shouldn't write similar there because we usually use similar as an actual meaningful word in a proof to say, hey, this case is exactly like the case that came before, so I'm not even going to write it down. It's not exactly like the case, but in just a general English sense, it's a fairly similar proof. See the text if you want. So we have that. It's a big law, the law of cosines that you've seen before. The reason I proved it is because we're going to use this to prove other things in the section. We've still got Heron's formula. We've got, I believe, Stewart's and Ptolemy's. So we'll get through those, I guess, on Monday's class, or as many as we can, and then we can jump into the in-circle, in-center, and all that good stuff. And of course, there's no class Friday next week because that's your exam day. I'll post some details about the exam tonight, but essentially think of it as a very limited time homework. It'll just be open all day Friday, and it'll consist of, I don't know, probably 3 proofs. One of the proofs I have in mind is a multi-parter, but yeah. Any questions? So keep an eye out for that. I'll make a campus announcement tonight. Yeah, otherwise, have a good weekend, guys. We'll see you.